Hey class, in today's lesson we're going to talk about using fundamental identities, which is found in section 5.1 part 2. Our objectives are to recognize and write fundamental trigonometric identities and to use fundamental trigonometric identities to evaluate, simplify, and rewrite trigonometric expressions. So in example 5, we are going to factor trigonometric expressions. So what you see below is 4 tangent squared theta plus tangent theta minus 3. I need you to recognize that we can actually use a substitution method that we use with regular quadratics, because essentially this is a quadratic expression. So in other words, I need you to recognize that x will be the same thing as tangent theta. So since x is going to be the same thing as tangent theta, let's first rewrite everything in terms of tangent theta. So this is 4 tangent theta squared plus tangent theta minus 3. Okay, tangent theta is x, so if I replace tangent theta with x, I get 4x squared plus x minus 3. All right, when we do AC after that point, AC becomes negative 12, and the factors of negative 12 that can give me 1 are positive 4 and negative 3. So we'll use positive 4 and negative 3 to replace this center value of x. So we would get 4x squared plus 4x minus 3x minus 3. Again, at this point, it feels just like a quadratic expression. If I take the greatest common factor of the first half, I would take out a 4x, and I'm left with x plus 1. If I take out negative 3x minus 3, I would factor out a negative 3, and I'd be left with also x plus 1. And that would leave me with the two factors, 4x minus 3 and x plus 1. Since I can't simplify those factors any further, then I switch it back out for tangent theta, which would give me 4 tangent theta minus 3 times tangent theta plus 1. And that is our answer. Let's look at our next example. All right, again, we are asked to factor the expression, and I want you to be very clear. This is just supposed to be secant squared theta minus 1. Again, this program for some reason writes it as secants, and it's really secant. Anyway, so secant squared theta minus 1. So again, if I use the substitution method, I can essentially say that x is secant theta. So in other words, what I see is secant theta that is squared and then minus 1. And if I trade it out, it becomes x squared minus 1. Well, we know that that's considered difference of squares, and the two factors you would get are x plus 1 and x minus 1. Since you can no longer factor past that point, we'll substitute the secant theta back in, and we'll get secant theta plus 1 and secant theta minus 1. And that will be our final answer. Let's take a look at our next example. Okay, so in example 6, we are asked to, again, factor a trig expression. So what we have is cosecant squared x minus cotangent x minus 3. Well, in this case, we are going to use substitution, but what I want you to recognize is that you have a cosecant squared x minus a cotangent squared x minus 3. Well, they are not the same, but in order for us to kind of continue to do the substitution method that we know, it'd be better to get them in the terms of the same term. Well, if you remember, cosecant squared x from the Pythagorean identity is the same thing as 1 plus cotangent squared x. So I can replace cosecant squared x with 1 plus cotangent squared x, and then now everything is in terms of cotangent x. So we want to look for those relationships. If I take everything out of parentheses and I combine this 1 with this negative 3, I'll be left with cotangent squared x minus cotangent x minus 2. Okay? From there, again, we want to use the substitution method and say that x equals cotangent x. Cotangent x. Sorry, that's a cotx. And so I'll replace them. So this becomes, again, if I just want to write this in terms of cotangent x, this is cotangent x squared minus cotangent x, and then minus 2. Cotangent x will be x squared minus x minus 2. AC, if we go from that point, AC of negative 2, that gives you negative 1, would be negative 2 and positive 1. So since the coefficient of x squared is 1, we can jump to the factors and say that they are x minus 2 and x plus 1 without doing the whole process. Again, you can only do that if your coefficient of your x squared is 1. If it's any other number, you have to go through the whole process like we did on the last example. We are done simplifying at that point, so then I can substitute my cotangent x back into my final answer, and that would be cotangent x minus 2 and then cotangent x plus 1. All right, let's look at our next example. Okay, in example 7, we need to simplify. We have sine t plus cotangent t times cosine t. Okay. Again, this is one of those situations where we want to rewrite a term if we can to make it easier or more simpler for ourselves. So the item that I see a sine, I see a cotangent, and then I see a cosine. If I think about which one of these does not belong, cotangent does not belong. However, cotangent shares a relationship with sine and cosine, and the fact that if we rewrite cotangent as the quotient of itself, then we'll have something different. So that quotient would be sine t plus, if I rewrite cotangent, I would have, instead of sine over cosine for tangent, I would have cosine t over sine t. And then again, that's times cosine t. All right, simplifying that would give us sine t plus cosine squared t over sine t. Okay, at this point, we have two fractions being added to each other, but they need to be, in order to add them, I have to be sure that they have the same denominator. So I'm going to multiply the first fraction by the denominator, which is sine t over sine t. Okay, that will give you sine squared t over sine t plus cosine squared t over sine t. That would then give you sine squared t plus cosine squared t over sine t. And again, we already know what sine squared plus cosine squared is, right? It's 1. So 1 over sine t then is the reciprocal function for cosecant t. Okay, and we are done with that example. Let's look at our next problem. Okay, in example 8, what we want to do is rewrite this trig expression outside of a fractional form. So typically when we want to change something out of fraction form, you have to multiply the denominator by the conjugate of itself, because conjugates, we know, will create just a whole number in the denominator, or some whole phrase. So I'm going to multiply this expression by the conjugate of the denominator, which would be 1 minus sine x. Okay, that would give us, for the numerator, 1 minus sine x. And if I use the box to do the denominator, which I don't have to do, but it's just helpful, I have 1 in positive sine x, and then I have 1 in negative sine x. That would give you 1 negative sine x, positive sine x, and then negative sine squared x. Okay, those are canceled, so it leaves me with 1 minus sine squared x. Now at this stage, please do not try to cancel out the ones and cancel out a sine or something like that. Because they are expressions, you have to take the whole expression as what it is to be able to simplify or cancel. And so in this case, because they're not either both 1 minus sine x and 1 minus sine x, or both 1 minus sine squared x over 1 minus sine squared x, you cannot simplify by canceling. All right, however, what we can do is that we know that the denominator is, from the Pythagorean identity, we know that the denominator is cosine squared x. So this becomes 1 minus sine x over cosine squared x. Okay, since that's the case, we can split the fraction now to have 1 over cosine squared x minus sine squared x over cosine squared x. And some of you may be wondering, well, Mr. Richardson, why don't we just split the fraction from the beginning? Well, I could have, actually, no, you can't. You can't split a denominator. You can split a numerator when we're talking about fractions with addition and subtraction. So again, we cannot split denominators like we see in the original problem, but I can split this denominator because the addition and subtraction took place in the numerator. All right, so 1 over cosine squared x is secant squared x, so we can go ahead and rewrite that moving forward as secant squared x because there's nothing else we're going to do with that. However, this minus sine squared x over cosine squared x, what we want to do with that, and did I say sine squared? I don't know how I got a squared. Let me erase that, this part right here. Okay. That'll be, it's just supposed to be sine x. I apologize. So it's just supposed to be sine x. Anyways, so we have sine x, it's minus sine x over cosine squared x. And again, what we want to do with this fraction alone is we want to split it. So this is still secant squared x minus, but what we have here is we have a sine x over a cosine x, because I can split that denominator, and it's being multiplied by 1 over cosine x. That's how we get the cosine squared x in the denominator. Okay. All right, so then from there, sine over cosine we know is tangent, and then 1 over cosine is secant. So as a final answer, you will get secant squared x minus sine over cosine is tangent x, and then 1 over cosine is secant x. And that is it. So we can close this off. And really, if we're talking about factoring, I could really take it one step further by factoring out a secant x. But if you make it to this point, just taking it out of fraction form, you have proved that it is out of fraction form. They didn't ask you to factor past that point. All right, and then our last example, example 9, it says, use the substituted value of x to simplify the expression below. So the substituted value that we have is x equals 2 tangent theta, and we're asked to substitute it into the expression square root of 4 plus x squared. This is pretty straightforward. Substituting is substituting in all forms, so we will take the square root of 4 plus x in this case is 2 tangent theta, and then we're going to square that, okay? So that would give me the square root of 4 plus, if I square both the 2 and the tangent theta, that gives me 4 tangent theta. Okay, from there, we should take out a greatest common factor of 4. And if we take out a 4, we have 1 plus tan theta left over. All right. And specifically, it's tangent squared. Don't know how I dropped the squared. And from the Pythagorean identities, we should recognize that 1 plus tangent squared theta is secant squared theta. So that'll give us the square root of 4 secant squared theta. And then finally, you can essentially take the square root of each. So I'm going to show them separated, but you don't have to. It's the square root of 4 times the square root of secant squared theta. You don't have to show this step, but the final answer would then be 2 secant theta. And we are done. All right, guys, we are done with this lesson for the day. If you have any questions, again, please be sure to come see me for tutoring.